In this video, I'm going to talk about how to show an indeterminate limit exists. What we talked about on the previous video is that if you get a limit and you plug in your x and y values and you get 0 over 0, if there's no algebra you can do to simplify this, the kind of default strategy is to assume that the limit doesn't exist and to start using your path technique where we go along two paths, try to get two different answers so that we can show that the limit doesn't exist. Well, this particular textbook we're using, they kind of mix some of these limits that don't exist with limits that actually do exist. So this particular one actually does exist, even though there's no way we can do any algebra to sort it out. So we'll talk about how to find the value of the limit. But let's suppose, just to, go through the thinking process, if you didn't realize that, a lot of textbooks will tell you if the limit exists, ours doesn't. So if you get a 0 over 0 limit and you start checking some pathways, so I would first start along y equals 0, because that passes through 0, 0. If y is 0, then your numerator is going to be 0. Your denominator, that would go away, would be 3x squared. We would get 0. Okay, that's all fine and good. If you tried x equals 0, you would have gotten the same answer. The top would have been 0 over 4y squared. So that would give you the same answer. So then I tried y equals x. And if y equals x, then the numerator, if you plug in x for y, would give you 2x cubed. And the denominator would be 3x squared plus 4x squared. But if you combine those, if you simplify it, you get 2x cubed over 7x squared. Of course, the x's cancel here, leaving you with an x in the top. And if x goes to 0, you get 0 again. We've tried some other techniques. What if we tried y equals x squared? Well, if you plug x squared in for y, your numerator becomes 2x to the fourth. The x squared stays the same. And then when you square the x squared, that turns into x to the fourth. So you would get this limit. And if you factor out the x squared from the bottom, that will cancel with 2 powers on the top, leaving you with 2x squared over 3 plus 4x squared. And once again, if you plug in 0, you're going to end up getting 0. So this is kind of frustrating because, as we know, there's an infinite number of paths to check. And our goal, move this up here, our goal, if we're trying to show the limit doesn't exist, is we're trying to find two paths that give us different limits. So far, we keep getting 0, but we know there's an infinite number of paths to keep checking that pass through 0, 0, and all it would take is one of those infinite paths that gives us an answer that's not 0, and the limit would not exist. So this is why in most scenarios, if the limit really does exist, they would have to give you some indication that it exists. Otherwise, we might keep trying these paths and we'll just keep getting 0, 0, 0, not ever knowing if if there is a path that gives us something other than 0. Okay, so our book doesn't give us any indication of that. So if you check a bunch of pathways, and this isn't foolproof, but if you do get 0, and I'll tell you in a little bit how you can tell if the limit exists in some cases. But maybe the limit is 0. So maybe you'll start changing your thinking now and say, hey, maybe that really, the limit does exist and the limit is 0. So if that's true, how do I show that? Okay. If the limit is 0, then as x, y, as our point approaches 0, 0, my function value should be getting close to 0, right? So let's consider the distance of our function from 0, right? If it's getting closer to 0, we can look at that distance. And remember that anytime you want to find the distance between two things, let's walk through this first. If I want to know how far between 3 and 7 on a number line, most people can just think about it and get 4. But if you think about it, you're really subtracting. You're either doing 7 minus 3, which of course gives you 4. But if you accidentally subtracted 3 minus 7 and got negative 4, well, as long as you take the absolute value, you're going to get the correct distance. So anytime you want to find the distance between two things, you subtract them and throw an absolute value around it. Okay, so for us, we want to find the distance between our function minus 0. Of course, the minus 0 just goes away. So we're just left with the absolute value of our function. Now, in absolute value, anything that's positive can go ahead and come out. And 2x squared over 3x squared plus 4y squared, that's all positive there. So I could pull that out. Y, however, could be negative. So I'm going to leave the absolute value on the y. Now, the technique we're going to use, we're actually going to go back to first quarter calculus and use the sandwich theorem, also sometimes called the squeeze theorem. And there's a little trick that comes up in here is that this 2x squared, notice that that is going to be less than or equal to 3x squared. I mean, certainly even just that's true, right? 2x squared would be less than 3x squared. And if I add a 4y squared, well, this has all the more reason to be less than this, okay? So now we could set up an inequality. Here's our function. Certainly that's going to generate values bigger than 0, right? If I greater than or equal to 0, possibly. And then this little trick here, if we want to find an upper bound for that, 2x squared, as we saw, was less than 3x squared plus 4y squared. So I'm going to replace that with 3x squared plus 4y squared. And now you can see my motivation for that trick was that these would cancel out and leave you with just the absolute value of y. So remember what this is saying now. The distance, this was our function. The distance between our function and 0 is sandwiched between these two things, between 0 and the absolute value of y. So if we take the limit as x and y approaches 0, 0, of course the limit of 0 is 0. The limit as x, y approaches 0, 0 for the absolute value of y, if you just plug in y is 0. So the limit of this function, our function as x, y approaches 0, has no choice but to be 0. So the limit must be 0. Now, given that, at least for our book examples, they're not telling us when we get 0 over 0, if the limit exists, there is a way, okay, let me read through this. How do we know if a 0 over 0 limit exists so that we don't go down the road of checking different paths and getting the same limit, not knowing if we should keep checking paths to show the limit doesn't exist, because that would be our normal strategy. Hopefully you will be told the limit exists if it really does. Again, our book doesn't. So if not, there is one telltale sign that I can tell you about that would indicate to you that, okay, this limit actually is going to exist and most likely will have a value of 0. If we go back to the example we just did here, it's got to look something like this. So again, I don't claim this is going to work all the time, but a lot of the limit questions kind of have a similar form here. The 2x squared times y, if you think about, I call this the total degree of the top. If I were to multiply these together, power-wise, that would generate a third degree, right? 2 plus 1. So I would call the total degree of the top 3. And the degree of each term in the bottom is 2. So because they're separate, I'm not going to combine them or anything, right? Both of those have a degree of 2. What happens then is if your limit has that form, if the total degree of the top is greater than the bottom, then the limit will exist and it will have a value of 0. This is something that actually can be shown in 21C, the calculus course for engineers and math majors. We actually do these limits and we use what we call polar coordinates, something some of you may have seen in a trig class. You can actually show that that limit would equal 0. We don't cover polar coordinates in the 17 series. So you're not going to be responsible for explaining why this limit is 0 using polar coordinates. Don't worry about that. But what you still will be responsible for is showing that the limit is 0 using the technique I just showed you by taking the distance from 0. Okay, so let me show you one more example. Okay, and this one's actually from the book. This is number 57. It's an odd problem, so the answer's in the back. 9.1. I've got the limit as x and y approaches 0, 0 of x times y over the square root of x squared plus y squared. Now that what we just talked about, let's think about the total degree. For the top, it's x to the first times y to the first, so I would say the total degree of the top is 2. The bottom degree looks like it's degree 2, but notice we're under a square root. So if you take the square root of something squared, that's really going to be acting like a degree 1 term, right? For example, the square root of x squared just by itself actually equals the absolute value of x to the first power, right? So it's acting like a degree 1 term. Since the degree of the top is bigger than the bottom, I know that this limit actually will exist. I don't need to bother necessarily checking a whole bunch of paths trying to show the limit doesn't exist, because it actually will exist and it will have a value of 0. So now this is what, okay, in 17C, don't answer your question this way, okay? Because this thing I'm talking about, degree, is not in the book, okay? What they're going to want you to do is first establish, okay, so let's do check one path. If we approach along y equals 0, the numerator is 0, the bottom is the square root of x squared, that'll give me 0, okay? Now, knowing what we know, that this limit will exist, we don't need to bother checking more paths, because guess what? We're going to get 0 every single path we choose. So we're going to set up a sandwich theorem inequality, and because the limit is 0, or we think it's going to be 0, we want to, again, set up the absolute value equation or expression for the distance between my function and 0, which is always going to be the absolute value of f of x, y minus 0. I put my function in there, right, minus 0. And then, like I did on the last one, anything that can come out of the absolute value is good. The square root of x squared plus y squared will always be positive, or at least at 0 at the worst. So we'll bring that out. And absolute value of x times y, you can break that up into 2 individual absolute values. And similar to the last problem, we're going to need to have some trick, some clever observation that's going to help us set up the inequality, particularly on the right side. So note that the absolute value of x, we saw earlier, that equals the square root of x squared. That's the definition. So if that's true, then the absolute value of x must be less than the square root of x squared plus y squared, right? Adding something here is definitely going to make that bigger, or at least equal to the absolute value of x. So now my inequality, my function definitely is greater than or equal to 0, and now I know it's less than if I replace the absolute value of x with the square root of x squared plus y squared. Again, why did I do that? You can tell, just like the last one, that's going to cancel out. It leaves me with just 0 and the absolute value of y on the endpoints. And of course, if I take the limit as x goes to 0, both of those will go to 0, which means my limit has to have a value of 0. I hope this helps. I know this is a little bit tricky, but hopefully this will help you.